In today's lab, we will study the rotational motion of a flywheel. First, we will see how the angular speed changes in response to a change in the moment of inertia by dropping a heavy object onto the flywheel as it is spinning. Next, we will measure the angular acceleration of the flywheel in response to a torque exerted by a hanging mass. Finally, we will measure the frictional torque on the flywheel and see if this accounts for any discrepancies between our measured and expected values. To accomplish these tasks, we will measure the angular speed of the flywheel using a photogate and the Pasco interface. Let's look at how a photogate works. The photogate shoots a beam of light between its two ends. When the beam's path is obstructed, the red light on the side of the photogate turns on. Mount the photogate in the stand and spin the slotted plastic disc. As the disc spins, the photogate light will flicker on and off. To set up the photogate in Data Studio, click on Channel 1 and then select Smart Pulley as your apparatus. Click on the Measurements tab and then select Angular Velocity Channel 1. Click on the tab again to change the units from degrees per second to radians per second. First, we'll look at what happens to the angular speed when we change the moment of inertia. We will start off with just the flywheel spinning. This has a moment of inertia equal to 1/2 times the mass of the flywheel times its radius squared. We will then drop the cylinder onto the flywheel as it is spinning. Its moment of inertia is mr squared. The total moment of inertia of the flywheel and the cylinder will just be the sum of their individual moments of inertia. Start the flywheel spinning and measure the angular speed of the flywheel. What is its angular momentum? What will happen to the angular momentum when you drop the cylinder onto the flywheel? What about the speed? Do your observations match your predictions? Next, we will measure the angular acceleration of the flywheel due to a torque from a hanging mass. To set up this experiment, cut a piece of string about 1 meter long and tie a large knot on one end. Thread the unknotted end of the string through the top of the outermost hole in the disc and pull the string through. Cut off any excess string above the knot. Mount the pulley on the edge of the table using the clamp. Check that the string from the disc is aligned with the pulley. Tie the free end of the string onto the weight hanger. The weight should not hit the floor when the string is fully extended. Mount the flywheel onto the axle. Check that the flat side of the axle is aligned with the flat side on the hole in the wheel. You are now ready to take data. Wind up the string on the flywheel and then let the weight go. As the hanging mass falls, it exerts a torque on the flywheel, causing the flywheel to accelerate. Let's calculate the expected value for the angular acceleration. We choose two coordinate systems. One for the hanging mass, upward motion is positive, while for the flywheel, counterclockwise rotations are positive. Use the right-hand rule to check the signs for the flywheel. Let's first take the case of the string unwinding. The tension exerts a torque in the negative direction on the flywheel. The magnitude of this torque is equal to r, the distance from the pivot point to the force's application, times the tension force. We then set this equal to the moment of inertia of the flywheel times alpha. For the counterweight, we sum up all the forces in the y direction and set these equal to the mass of the counterweights times their acceleration. As the weight accelerates in the negative y direction, the flywheel will also accelerate in a negative direction. Therefore, the angular acceleration and the linear acceleration have the same sign. The magnitude of the linear acceleration is equal to r times the angular acceleration. We can use this constraint to relate the motion of the flywheel and the mass and solve for the angular acceleration of the flywheel. We can follow the same careful procedure to find the angular acceleration when the string is winding up. Plug in your measured values for the different radii and masses to come up with an expected value for the angular acceleration. Let's look at the data that you will take using Pasco. When the weight switches direction, the slope of the angular velocity changes signs. To find the flywheel's angular acceleration, apply a linear fit to the angular speed for both the upward and downward motion. The slope of the angular speed is the angular acceleration. Perform fits on at least 5 cycles and take the average of the slopes to find the value of the angular acceleration for the upward motion and for the downward motion. How do these values compare to your predictions? To measure the frictional torque, start the flywheel spinning and record the angular speed over time for at least 1 minute. Then find the slope of the angular speed. How does this relate to the frictional torque? Does this torque explain any discrepancy between your predicted and measured values for the angular acceleration?